Welcome back, everybody, to the Optimus Process Solutions webinar series. Today, we will be discussing kiln mass and energy balance, and we will have our guest speaker today, Roland Sutter, speaking. Roland is our chief engineer in the Optimus Process Company. He's got 40 plus years of experience in mechanical and process design, fabrication, operations, installation, and troubleshooting rotary processing equipment. He's written many technical articles, all pertaining to your rotary equipment, such as kilns, dryers, ball mills, grinding mills, etc. He's presented over 100 plus lectures, seminars on rotary equipment topics. So today, we're going to be talking about kiln mass and energy balance today, Roland. So can you go into a little bit of detail on this?
Yeah, right, Tom. I think that the value of this is if you have an operating system out in the field, you can make certain measurements. You can diagnose some of the problems you may be having and increase your efficiency or other factors in your process. So one technique is to do a heat and mass balance using certain parameters measured in the field. Mm-hmm. And then based on those numbers, do various calculations to come up with the heat and mass balance.
I see. So we're going to start on the combustion end a little bit.
Well, yeah. First thing you want to look at is the gases generated in the combustion process on the discharge end of your kiln. Mm-hmm. And these are all basic equations that we use that have been verified many times.
I see.
It's called chemistry.
I see. And we're just showing the fire and the flame right now.
Yeah, there's the flame we'll be dealing with, and that's a very good picture of combustion.
Yep.
Heat and mass.
Okay, so guiding principles, Roland.
Yeah, essentially, stuff that goes into the kiln, it's got to come out of the kiln.
I see.
Very technical, astute observation.
Right, but isn't that the first law of thermodynamics?
Yeah, that's what they call it.
I see.
And the heat that enters the kiln has to leave the kiln.
Very thought-provoking.
More thermodynamics.
I see. So can you tell me a little bit about this chart or this figure?
Just what do we have to measure, or what can we measure? And generally, with the proper instruments, you can make these measurements in the field. And that's the primary air going into your burner tube.
Right, on the right side here.
Yeah.
Okay.
You should be able to know what the fuel rate is. Mm-hmm. And we're mainly talking about combustion now. Mm-hmm. There's additional air that comes through your cooler called secondary air. Mm-hmm. And there could be some air leakage at the seals, but not shown on this picture.
Okay.
But essentially, that's where you can, from these variables, you can calculate the mass of material going into the kiln with respect to combustion only. Mm-hmm.
Okay. And then we got some of the...
And then once we get through that process, obviously you're trying to calcine something. Mm-hmm. And by definition, calcining means you're changing the chemistry, the material coming in with respect to the material going out. So there must be some reaction, whether it's endothermic or exothermic. Mm-hmm. There's some chemistry involved. So it takes heat in calcining to make the process go, and certain products are generated. It might be water vapor. It might be
carbon dioxide.
So you have to add those gases to the combustion gases.
Mm-hmm. Okay.
And then once you have the gases from combustion, the gases from the process, you will know what the gases are exiting your kiln.
I see.
That's the mass balance. Now the heat balance, obviously the material coming in has a certain temperature, which normally would be ambient, but not necessarily. It comes into the kiln, gets heated up to like 2100 degrees or some temperature you desire, and takes heat to do that. So that's a heat loss.
I see.
That heat is a loss to the gases in the kiln.
Okay.
It goes into the product. Okay.
Okay.
But it's still there. What went in has to come out. So when the product comes out of the cooler, the secondary air got heated up by the material to cool it down. So all these interactions, is how you develop a heat and mass balance.
Right. So these are all small pieces that we've all combined together. Okay. Right. So when we're out in the field, can you expand a little bit on the field?
Well, depending on your operation, this would be basic for most kilns. You should be able to measure the primary burner air rate, primary air.
Okay.
If you have a contact cooler or you have a grate cooler, you should be able to measure the secondary air and its temperature.
Okay.
You should be able to know the composition of your fuel. You should know the rate that you're feeding fuel into the kiln and what temperature that feed goes in at. Something we'll get into later, there's a lot of combustion air involved in that, and air has humidity, it's not dry, and that has an effect on your system.
Okay, and these are all the stuff that goes into the system.
Right, and then if you have a lousy seal, you get a bunch of air leakage, which defeats the whole purpose of your burner.
I see.
As far as outputs go, the product rate and temperature should be able to measure all the doing thermal scans. You should be able to measure the temperature of the external surface of your system and thereby calculate the heat loss. You should know what chemistry is going on in your kiln.
And some can be simple, but others can be kind of complicated.
Some of it can be simple. Some of it can be multiple phase changes. But essentially, that's something that your chemistry department should know since you're in that business.
I see.
And we generally can help you with that if necessary.
Okay.
And from that, we want to calculate the mass of the exit gases. That's our primary objective here.
I see.
And calculate the amount of heat going into the kiln.
I see.
So in order to have those two numbers, we got to do a balance.
So what we're looking at now is kind of a pie chart of all the heat being broken into smaller pieces. Right.
This would be we just threw this in. You'll see it later, but you can see in this particular case, which is an alumina kiln, 37% of the heat consumption is the process.
Right.
Which you cannot really change.
Right.
7% of it is evaporating water, just heating water from 60 to 212 degrees Fahrenheit. And then, we're going to go over 212, so we're going to boil water, and you're going to consume 1,000 BTUs approximately per pound of water.
Wow. So Roland, just heating up water and then evaporating water is about 15% of the process.
Yes, sir.
So if, let's say we have a drier material going in or drier air going in, will that help?
Yes, that would help. However, generally you can't do much about it because the only source of oxygen we have is the atmosphere.
Yes, so depending on where you're at, it's either...
maybe drying the material before you put it in the kiln by some other efficient means would be a good idea.
I see.
Because kilns are not very good dryers.
I see.
Functionally.
I see. Okay.
So it would be best if you reduce the moisture content before you even put it in the kiln, so you didn't have to evaporate water.
Mm-hmm.
You can do it much more efficiently in a dryer.
In a dryer than a kiln, I see.
Right. And let me see, we got 1%.
Oh, actually, take that back. This water is this part, so the water is 9%, and then the solids, heating it from 60 to 428, is 7%. My bad, but 9% is still fairly significant.
Yes. And then we have to heat the solids up to from the feed temperature to the initiation of your reaction in the kiln, and then it becomes a different material. So then you have to heat it up from the reaction temperature to your final temperature.
I see.
So
so for example, on the alumina kiln, the 428 and the 2100, these are just breaks in the chemical changes.
Right, that's where the reaction occurred.
Okay.
And it came from aluminum trihydroxide to alumina.
Right. Okay. So we got the infamous combustion triangle.
Right. So what is combustion? Combustion is a reaction whereby a material is oxidized and generates heat. And you have, we're talking about hydrocarbons in general, and it's composed of carbon, hydrogen, a little dash of nitrogen, a little dash of oxygen right in the material, add some sulfur, which isn't usually a big number.
Okay.
In order to have combustion, you have to ignite the fuel. So you need a spark or some sort of pilot or some way of igniting it, because it needs an initiation of energy to start the combustion process. And during this process, the oxygen combines or oxidizes the hydrocarbons and generates carbon dioxide, water vapor, sulfur dioxide. And if you put excess oxygen in, more than you need for the chemical reaction, you'll wind up with some oxygen and nitrogen. And nitrogen is something that, using air as the oxidizer, you get, for every pound of oxygen, you get 3.31 pounds of nitrogen free.
I see.
Useless nitrogen.
It doesn't carry any heat or anything.
It doesn't do much. All it does is consume heat.
Oh, I see.
Okay.
So if theoretically they run out of pure oxygen, it would be much better.
That'd be called a acetylene torch.
I see.
So anyway, air is a good source of oxygen. So you're going to get diatomic oxygen and diatomic nitrogen in the combustion gases because you used air.
And diatomic just means two, right? Two molecules of oxygen. Okay.
And if you don't do a very good job of combusting, you'll get carbon monoxide, which means that's an incomplete combustion. And due to the fact that there's nitrogen in there, you can generate NOx, which is nitrous oxides of various forms.
EPA does not like them.
You wouldn't like them, I don't like them, and we try to eliminate them, but that's just part of combustion.
I see. So you got so really to summarize, you'll need the fuel and the air with an ignition point to generate the flame, to create the heat, and all the molecules on the right are just exhausts or
that's what's
products
coming out of the feed end of your kiln as exhaust gas.
Okay.
Now, what kind of fuels? A common fuel is coal, natural gas, heavy oil, and petroleum coke. That's normally what's used in kilns. You can use those fuels in combination or as a single source. And once again, no matter what they are, they're carbon, hydrogen, sulfur, nitrogen, and oxygen.
I've had some questions on the sizes of the solids. Is there a particular size of the solids that?
Generally, whether it be petroleum coke or coal, you want to grind that down to about 200 mesh or better,
Mm-hmm.
because you have to blow it in with the primary air in the burner tube.
Mm.
And if the particles are too large, it takes too long for them to burn.
Right.
So the finer they are, the quicker they burn,
Mm-hmm.
the more luminous flame you get.
Mm-hmm.
So you want the fuel to be dry and a particle size below 200 mesh.
I see. So this is the ultimate analysis of the fuel?
Right. Usually you get this from your supplier.
Okay.
And if he gives you some other method of analysis, that's all right. But tell him you want the ultimate analysis. You want to know how much carbon, hydrogen, sulfur, oxygen, and nitrogen there is in the fuel.
Right.
And these are just examples. It varies. Like we have nitrogen. This is a particular natural gas in Birmingham, Alabama area. If you go to northern Pennsylvania, you'll find more sulfur. You can actually have sulfury gas, no nitrogen. So it varies depending on the deposit.
So of these 5 constituents, is there a particular one that you would want if you're looking for a particular fuel? Like, you want more carbon? Do you want more hydrogen?
Well, I want more hydrogen.
Mm-hmm.
That has the highest heating value, which we'll get to in a minute.
Mm-hmm.
You almost get 55,000 BTUs per pound out of hydrogen, and much less out of carbon per pound. But it has its downfall because it generates water. And so you can see the heating values. There's a term called lower heating value. That's the number you always want to use, because there's another term called higher heating value or gross heating value, which means that the hydrogen, which turned into water vapor, is condensed, and then it makes that number look bigger.
I see.
So, something with a lot of hydrogen, the effect on the heating value goes up as the hydrogen increases.
So then on this one, I see the lower heating value. It looks like natural gas is the highest.
Yeah.
And coal tends to be the lowest. And I understand a lot of people are switching over to natural gas because it's cheaper. Are there any other considerations with natural gas?
In particular, the kilns.
Okay.
Due to the fact that you have these particles being burnt with coal and pet coke, they generally give you a much more luminous flame, which effectively gives you more radiation heat transfer to your bed of material in your kiln.
Right, so it's a brighter flame.
It's a brighter flame, yes. So it has, coal and pet coke have their advantages, but that's not to say you can't burn both at the same time.
I see. You
can have a natural gas flame with some pet coke or coal and get both of the best worlds. Okay, which is probably a good idea to consider.
Mixed fuel.
If you're going to natural gas, maybe you need to maintain a little bit of solids in that gas to get you better flame. So as I was talking about before, this is all basic chemistry. Take carbon and oxygen, make carbon dioxide. 1 pound of carbon will result in 14,000 BTUs per pound. And
you always want a higher BTU per pound.
Right. And on a pound mass, you take 1 pound of carbon, 2.66 pounds of oxygen, you get 3.66 pounds of CO2. And you will notice that the 1 and the 2.66 do add up to 3.66.
Yes.
And that's important.
Yes. Otherwise, we're violating our first principles in the beginning, right?
Right.
Okay.
So that is derived from the molecular weight of the particular element, carbon being 12, oxygen being 32, and those numbers on the left side have to be the same as the number on the right side. Okay.
And all this is pretty much the same thing. It's just a different measurement in a way.
Right. Some people talk about moles. To me, that's something I have in my lawn. And I like to use pounds because that's something I can understand.
Right, all the chemistry people don't worry about that, right?
Right. Anyway, the same thing applies to hydrogen. For 1 pound of hydrogen, you're going to get 51,000 BTUs. And SO2, you can see it's like 4,000. So this is all the same theme. It's just chemistry.
Yeah, just a little different characteristic depending on what it is.
There are some other factors in here that coal isn't 100% coal. It can have shale in it. It can have moisture in it, or other things, silica rock. So a pound of coal isn't a pound of maybe.
So you
put in a bucket from the pile. There may be a lot of other things in there that you won't burn.
So you really want to get the chemical composition from your shipment.
Yeah, you might be heating up rock. Okay.
Which
and
will do
a lot
nothing.
of people, when a coal truck comes, they wait until it rains before they deliver. So if the moisture content's high, it's very costly in this process. And you have to dry it, maybe in your grinding system.
So you're telling me a very practical thing to do right now is to know the chemical composition of my fuel.
Yes.
Okay. So this is a more pictorial view.
It's just a picture of what we've been discussing, that you have this phase of what we're discussing is to calculate the mass of gases coming off the kiln at the firing zone. And that is air leakage, which we'll get to later. That's a big negative. You need primary air to get enough velocity in your burner to transport the fuel. And secondary air, since you have this material at 2100 degrees, and it's probably a good idea to cool it down before you put it in your cupboard.
Right.
You might as well gain that heat by cooling the material, the product, for 2100 degrees to some reasonable temperature. So that's where the secondary heat comes from.
Okay. So stoichiometric
now we got
ratio.
This big word, stoichiometric. Okay. Well.
Sounds German.
Yeah, it does. Well, I don't know what that all means, but essentially what it does mean is, in a perfect world, if you added the exact amount of oxygen per our equations that we just went over to burn all the hydrocarbons and not have any oxygen in the gases when you were done, that's what stoichiometric means. So if you hear that word, I can't usually spell it. I usually get it wrong every time. But anyway, when you go through those numbers, there's a little equation for you. It's the same things that I showed you before. 0.266 times the percent carbon.
And this is just for the perfect condition.
Right. So anyway, you go through their little formula, and the stoichiometric air, you're still going to get that oxygen. When you want the oxygen, you're still going to get the nitrogen. So you're going to have to add the combustion products plus the nitrogen with the air, and that'll give you your combustion products.
Okay.
Why do we even bother? Okay, go to the next one. We want to try to figure out what kind of flame temperature we can get, because if we're going to heat some material at 2100 degrees Fahrenheit, I think we're going to have to have something a little higher than that to get it up to that temperature, according to theory anyway.
Right.
So we have a difficult time measuring flame temperatures.
Yeah, a lot of thermocouples tend to get burnt.
They don't last too long. A flame isn't a consistent in the core of a flame, the temperature is not the same as on the outside.
Right. That's like if you had a flame and it's got different colors inside.
Right. So it's a difficult thing to measure. But what we can do is we can approximate what that temperature would be under certain conditions.
Okay.
And those conditions are the atmospheric pressure, stoichiometric oxygen with air, as air being the source, and no losses to the external losses off the flame. In other words, by heating up the refractory, I'm not considering any losses from that flame. So in that case, if I put in a certain heat input, say I'm putting natural gas in at 19,000 BTUs per pound, and I got 1,000 pounds, okay. If I go and calculate what the CO2, O2, there's no O2, the N2, all the gases that are coming off the flame, and figure out what their heat content is, those two numbers should be the same.
I see.
If there's no losses to the environment.
Right, and that's where the adiabatic flame temperature comes
It means
in.
there's no losses to external areas. Okay.
I see.
So we know what the heat content of various gases are. You can see there that
as you increase the temperature,
and that water really is bad stuff, isn't it?
Yes.
All the other ones look reasonably close together.
And water just shoots up.
Water is really a heat sink. So another word to the wise that heating water is not a very good practice. So
very expensive.
That being said, so anyway, if I take so many pounds of all these gases and apply the heat content in BTUs per pound, because I know how many pounds I generated, and that when that number is equal to the input heat, that's what they call the adiabatic flame temperature.
I see.
Of course, I don't do this by hand anymore. So up there in the left-hand corner, we put in into a little Excel program, not a complicated computer program by any means. We put in the composition of natural gas.
Right, so that's the yellow up top here, right?
And going over to the left, to the right, excuse me, you'll see that we calculated the products of combustion.
Right.
So many pounds per pound of fuel. And where the error is, that's saying there's no excess air.
Hence, stoichiometric
conditions.
Right.
And right above that to the right, I know how much oxygen I need.
This is the stoichiometric
oxygen required. So if you get down below the error, you're going to see total oxygen is 3.63. Okay, now I got to add 3.31 times that in nitrogen. Okay, and add them up. That's how much air I'm putting in. The total air is 15 point something or other, 6.5. Okay, that being said, if I go over here to the right in that table, the volumetric analysis, I'm noticing that O2 is 0. Okay.
Right.
So that's what will be coming out of your kiln. No oxygen. That's stoichiometric conditions, which never occur, but we'll deal with that in a minute. But we got to start somewhere.
Right.
So, and I'm putting in 2,500 pounds an hour. So
of fuel, right?
Of fuel,
okay.
Which results to a heat input of 48 million.
48 million BTUs per hour.
And there's no secondary air. Right above that, you can see that the secondary air temperature is room temperature. Okay. So anyway, when those two numbers, that 48 million and 48 million,
and on the bottom, right?
Yeah.
And this is the gas.
That's the heat content of the gases.
Right.
That's the heat input. When those two numbers are the same, that is stoichiometric temperature, and that is
3668 degrees Fahrenheit.
Right.
And then
there's a little table up here
on the right here.
Yes.
Okay.
These are typical numbers that have been measured in a special chamber.
Mm-hmm.
Natural gas come out to 3,500 degrees.
Yeah, 3562.
And I think the highest one was coal.
Yep, 3957.
Right. So what happened there, it's an indication of the luminosity of the fuel too.
Right. So
not
this
only
is
the temperature.
So this is back where you're talking about coal tends to have a much brighter flame
Right.
versus natural gas, and you see this 400 degree difference.
Right.
Okay. So this is when you talk about the secondary air being heated?
So whatever you do, if you can find a source to heat that combustion air before it goes into the kiln,
Mm-hmm.
and that's generally a contact cooler on a lime kiln, on a
satellite cooler,
a pebble lime kiln, satellite cooler on a paper mill mud kiln,
mm-hmm.
or a rotary cooler on some other processes. Whatever you have, you want to heat that secondary air up, because effectively the mixed air gas temperature, this isn't necessarily the flame temperature.
Right, so the gas temperature and the flame temperature are different.
Yes.
Okay.
Effectively.
Mm-hmm.
It's hard to measure flame temperature.
A little bit.
In reality. But once the gases get out of the flame, a thermocouple will survive.
Yes, or at least long enough to take.
You don't want the thermocouple to be part of your combustion process.
You have to do heat mass
Furthermore,
balance on that.
there's all kinds of gradients in a flame. The center isn't the same as the outside. And you can only see the outside, so essentially the outside surface of the flame is all that your process sees. It doesn't see what's going on in the flame.
Right.
But anyway, if I, typically on a pebble lime kiln, you might be pushing 1,000 degrees Fahrenheit secondary air, and effectively that would almost increase your flame temperature to 4,000 degrees.
Wow.
On the opposite of the scale, if you don't cool it, don't heat up the secondary air, which could be air leakage, because I don't want to go to tertiary air.
Mm-hmm.
All the air coming in is secondary air if it doesn't get through your burner pipe. You can see from this diagram that if you went 100% excess air,
you can drop what? 1,500,
1,500 degrees.
It's quite significant.
So this is not good.
So if you had a process that needed to be 2,800 degrees Fahrenheit and you had that kind of leakage,
forget it. Now, one thing that we measure, we have an analyzer you can buy. You measure the O2 coming out of your excuse me. The O2 coming out of your kiln on a dry basis, not a wet basis.
Dry meaning no moisture.
No
in there,
moisture.
Right? Okay.
Doesn't consider the moisture.
And most portable ones are dry bases.
Right. As you increase the air above stoichiometric, the oxygen level goes up. Most kilns are operating down around 1 to 2%. Okay. Dry. And that's a reflection of your excess air, which is very hard to measure because you don't know the air leakage. So anyway, that's something we'll consider later, but
so
oxygen is a primary measure of the health of your kiln.
So in most kilns, you want it in that 2 to 3% range.
Right. If we go the other way and we don't put enough oxygen in, we're going to generate carbon monoxide, which is not good.
Right.
And even if your burner isn't operating right today and you're getting a little bit of carbon monoxide off of it, as long as the temperature is 1,128 degrees and it's Fahrenheit and it has some oxygen present, you can still burn. It'll auto-ignite and it'll burn down the kiln further. So sometimes you can get a hotter flame in your, the flame temperature can be higher because you reduce the oxygen, and you might get a little carbon monoxide off the flame, but you'll get a hotter flame.
Interesting.
So there's other things going on here, which that's why it's so important that your oxygen level be as low as you can get it, and not exceed 100 parts per million
on the carbon
of
monoxide.
carbon monoxide.
And
So that's something you're playing with, and it's not that easy. But you're always trying to get the hottest flame temperature, which is the lowest oxygen or air, and the air at the highest temperature. All those combined together at the lowest oxygen level is where you want to be.
Right.
With the minimum of a reasonable amount of CO.
And the CO can be measured with a handheld gas analyzer too, right? As
long as it's measured in the kiln.
Measured in the kiln, but not at the...
not after the seal.
Not after seal, not at the exhaust hood.
Right.
Because then you have all sorts of other leakages.
You got leakage everywhere.
Right.
Another thing I think we covered, on a humid day, actually the amount of air, water and air can be significant. So any of that, you got to take that into account.
Right. So Louisiana versus Arizona.
Right.
You could be heating an extra 5-6 million BTUs.
Right. So anyway, we drew some fancy little flames here, and we talked about adiabatic flame temperature and heat loss to the charge and surrounding will affect that actual theoretical temperature. Also, another factor that comes into play is the flame is so hot that the water can actually break down and go back to hydrogen.
Oh, wow.
It's called dissociation.
Oh. And
the carbon dioxide can actually break down, even though it's been burnt once. It gets so hot in there, it actually dissociates and becomes carbon again and then reburns.
So is dissociation a beneficial or?
Well, it actually reduces what we, it's one of the differences in adiabatic flame temperature versus real temperature, because once that breaks down, that hydrogen burns after the flame.
Wow.
Okay. So even though it's an insignificant amount, it affects this theoretical flame temperature called adiabatic. Okay. It's not to be confused with reality. It's, it might be 100 to 200 degrees lower than the predicted number. It's in the range, but you're going to have this dissociation, which will cause actually a reduction in heat output, because it's actually converting it back into the elemental form.
Right. So you're losing
heat. So when we talk about adiabatic flame temperature and actual flame temperature, they're two different things, but they're not that far apart.
Right. Okay. So we got some flame shapes here.
Right. Okay, the one on the top. Okay. You got to keep this in mind. You got this pipe that has a high velocity of air coming through it. That's called the burner pipe. You have this secondary air coming in from the cooler, which the draft on the ID fan's pulling through the cooler, or if there's a booster fan on it, you're pushing air through this bed of material. It's picking up heat, but when it gets to the kiln, it's not a high velocity. Okay.
Right.
So the secondary air is like an envelope around the flame. And it takes time for that oxygen to go into the flame and result in combustion. Okay. So in the first picture, if the velocity in the burner is too low, the envelope of the secondary air coming around will cause the flame to go hunt for oxygen. and it'll actually get bigger and bigger, and that's what we call a bushy flame.
So that's too much secondary air?
Not enough velocity.
Not enough velocity in
Right.
the primary air going through.
Right.
Okay.
On the other hand, you talk to the engineer, and he said, well, let's increase that velocity.
Mm-hmm.
So he said, okay, and I really whipped it up.
Uh-huh.
Okay, now I have too much velocity in the burner tube,
Mm-hmm.
and secondary air looks at it, and it's gone before I even get to it. So you get a real long flame, okay, which is very inefficient. Going back to the first flame, actually that can be damaging to your refractory, because if your flame impinges on your refractory, it'll just spall it out. Okay.
So if you have refractory losses, these are some of the symptoms you want to look at.
Causing that. And the best is obviously somewhere in between. And I can't tell you what that is. But somewhere in between those two configurations is where you want to be.
Mm-hmm.
And generally speaking, I know it's hard to measure, but the flame length should be about 3 diameters of the kiln diameter.
So if it's a 10-foot kiln,
I ain't going in there and measure with my tape.
So if it's a 10-foot kiln, it's about 30.
Well, if you use go outside and get your optical camera and you look at the side of a kiln, you can see many times, if there's not too much refractory in there, you can actually see that the temperature of the shell is high and then
gets lower.
It cools down.
So if
you can pretty well tell what the flame length is with the camera.
So you can use like a thermal camera, thermal imaging, and then kind of see your temperature profiles.
Because at the tip of the flame, it's pretty well over. You know, you're not getting as much radiation. You're going to see that profile on the side. It won't be very distinct. You know, a lot of times with the camera, you can actually see the spaces between bricks. Right? Because of a temperature difference. But you're going to see this flame too. Oh. I can't say you'll see it on everybody's kiln, but it's generally there.
See.
So okay, most of the heat transfer in a kiln is radiation heat transfer, which we discussed before is like T to the fourth. So as the temperature goes up, the energy is the horsepower, and generally in a kiln, the gas velocity is very low because you don't want to blow the material. It's not a dryer, right? So there's no reason to have high velocities because convective heat transfer ain't going to help you. So 95% of the heat in a kiln is radiation heat transfer. And we estimate 5% convective. And, okay, where does this radiant heat transfer come from? Well, the carbon dioxide and the water vapor in the gases are the highest sources of radiation. So the more CO2 you got, the more water vapor you got, the better heat transfer you're going to get. Okay. And from the gases to the bed is one mechanism of heat transfer. The other one is the refractory gets heated up, and the refractory also radiates back. It radiates from the gases to the refractory, and then from the refractory back to the bed. So there's two mechanisms going on in there as far as radiant heat transfer goes. And then you can get conductive heat transfer. That's simply conduction between the refractory into the bed as it passes over the refractory. And that isn't very significant, but
worth mentioning.
You can actually measure it.
So a little bit on sensible heat versus latent heat.
Okay, so far with what we went through, we were able to calculate the pounds of exhaust gases going out the kiln, right?
Yes.
Okay. But we don't know what the temperature is. Okay. We can go measure the temperature very easily with a thermocouple coming off of kiln on the exit gas temperature, right? Okay. But we're going to see if that temperature works out with our balance. So we know how many pounds of gas is going through the kiln. We know how much heat's available in those gases, right?
Mm-hmm.
Okay, now where are we going to lose gases? Well,
going through the material.
Yeah, we got what we call sensible heat.
Mm-hmm.
I don't know where that word come from either. It's just hot.
Yep.
Anyway, if you take a piece of a brick,
mm-hmm.
you heat it up to 1,000 degrees.
Mm-hmm.
It takes a certain amount of temperature to get there.
Right.
A certain amount of heat, right? And how we measure that is the difference in temperature between when it was cold and when it's heated up,
mm-hmm.
times a factor, which is called the specific heat.
Mm-hmm. And that you can look up on a table.
Yeah, that's pretty well information that's available on the internet or wherever you want to go. So you just take the specific heat times the mass flow times the temperature difference, and that gives you the heat loss. Well, if we were heating limestone up from 75 to 1,000 degrees, we can figure out what the heat loss is, right?
Mm-hmm. Right.
And he also told you that after the process, the calcining process occurs in the kiln, the material isn't the same as it was before that because of a chemical change. You have to go in and look at the specific heat of that material heated up from 1,000 degrees to 2,100 degrees or whatever final temperature you have. So that's what we call sensible heat. And that would apply to limestone, alumina, any solid material. They're pretty simple, right?
Right.
Okay, then we have another process going on in the kiln, which is water. Water has sensible heat from 1 degree to ambient up to 212, right? And the specific heat is 1.
Right.
Okay. However, when you go to boil it, there's a phase change, as we all know, and that is called steam. And that takes 970 BTU. So if a feed coming in is wet, I'm going to have to evaporate water.
Right.
Okay.
So
that's another loss.
To kind of summarize a little bit, the sensible heat normally means if temperature change occurs. So if you go from 75 to 1,000 degrees, your temperature is changing. But latent heat, if it means phase changes or something's changing, but temperature is not changing. When you're boiling water, it's consistently at 212. So, but it's changing phases. You still need heat. That's what latent heat means, right? Okay.
Now, if you go above 212, then you're heating a water vapor, and it has sensible heat too.
Right.
And it's not a phase change.
Right.
It's just heating water vapor. And we showed you that chart where the heat content of water vapor is relatively high compared to anything else.
Yes. Okay. And then these are just some of the other losses in the kiln. So the process, the chemical reactions, so we got some simple ones that you want to discuss?
Okay, we just picked 2 out. There's many. Probably the most common is limestone, making lime. It almost applies to cement too because you're doing the same thing in a cement kiln, but it's more complicated.
It's got a lot more components.
Right. But essentially you're taking limestone, which is CaCO3. It's a high cal limestone. Apply heat to it. For 1 pound of limestone, you get 0.56 pounds of calcium oxide, which is lime, and you get 0.44 pounds of CO2. Just like combustion, right? But it's not.
Right. And then you do the same with aluminum trihydrate.
Yeah. And then you got to put heat into to make this happen, and that's 1,387 BTUs per pound. So there's a heat loss, and there's a mass of carbon dioxide that I have to add to my combustion gases to get the final gases coming out of the kiln.
Right, so that's part of your process gases.
Yeah, that's part of the mass. And alumina is the same way.
Okay.
Alumina, all we have is water generated. Okay. There's no CO2.
Right.
Once
Okay.
again, you have to add whatever water vapors evolves from the system,
Right.
that you have to add that to your combustion gases to get the final exit gas mass.
Right. So now, when it's all said and done, we got all the gases balanced now. We got all this stuff going in, and now we know what's coming out, following first principles.
Right.
So we got the fuel and primary air, leakage air and secondary air, the water in all aspects of the system, and the combustion air and the feed and the process water that's generated in chemical reactions. That's a very significant amount. And then obviously the process gases generated, like the carbon dioxide. And then once you add all that together, it's the exhaust gas.
Right. And so far, it hasn't been that difficult calculations.
Mm-hmm. Each individual one's just
right.
additions, multiplications. So now we get into the losses on the external side.
Right. So anyway, we essentially have two modes of heat transfer from external surfaces, which includes the kiln,
Mm-hmm.
the firing hood,
Mm-hmm.
the cooler, and any ductwork thereof that's got a significant temperature.
Mm-hmm.
So there's heat losses everywhere. Okay.
Right.
So anyway, but still, if you take a heat gun and you get the temperature, you can figure out what the radiant heat loss is from a surface.
Right.
And that's simply the formula shown. And we keep coming up with this T to the fourth all the time.
Mm-hmm.
So there's a formula related to heat transfer from a surface, which is going on in the kiln too.
Mm.
So anyway, there's a factor on there called the emittance.
Mm-hmm.
And the emittance is very close to what they call emissivity. It's almost the same thing.
I see.
And when you shoot this with your camera, you got to get the right emissivity to set your gun for.
Mm-hmm.
And on a kiln, that's usually about 0.79.
Mm. Because of carbon steel.
Because it's rusted.
I see.
So it's important that you get the right emissivity. So you might have to do some, just take a thermocouple and put it up on the shell.
And then compare it to the IR.
Compare it to the IR to get an idea, because you want to get this right. I mean,
right. So what you're saying is if you just go up and just use your infrared gun and just click it and just get a temperature, that might not necessarily be right.
Because of the emissivity.
Because if it's a shiny surface versus the rusty surface, most kilns have a rusted surface. So like a tire versus the shell, just the emissivity can give you differences.
Right.
Okay.
I mean, it's emissivity could be anywhere from 0.95 to 0.01.
Right.
So, but commonly it's in that 0.79 range.
So this is an example of a shell scan that we do.
Right.
So as you can see here on the bottom, you can use the emissivity 0.95 or something else.
Right.
This is just an example.
Okay, once you have these numbers, you have your scan, you can go calculate what the estimated heat loss is from your shell.
Mm-hmm.
And hopefully you won't find a hot spot at the shell.
Yeah, so for example, on this one, on the left, it's the discharge in, on the right, it's the feed in. So on the left, you'll see that it tends to be a lot redder than on the right. So maybe somewhere on the left, that's where their maximum flame temperature is.
Right.
So these are some examples.
So yeah, we don't want to belabor you with all the formulas, but this is just a simple Excel spreadsheet.
Mm-hmm.
There's no real big computer program involved here.
Mm-hmm.
We're trying to keep this as simple as possible.
Mm-hmm.
But you can see, we're going through and figuring out what the wet feed is and how many BTUs to as we discussed,
Mm-hmm.
how much BTUs we estimate for all these functions to be taken care of, and including the shell temperature over on the right, and how many square foot area, whatever.
Mm-hmm.
So what we just told you is all the spreadsheet does,
Mm-hmm.
but you need the input to get it right.
Mm-hmm.
Okay.
Yep.
And just to reiterate, we're talking about primary air, fuel rate, secondary air, the process, the heat losses from the surface. In the end, what we get is the exhaust gases.
Right.
And we know how many pounds of CO2 there is, oxygen, water, etc.
Mm-hmm.
And from these numbers, you can actually calculate the ACFM or SCFM, you so desire.
The actual
flow at temperature
or the standard
conditions using these numbers.
Right.
And it gives you a good idea what's going to your ID fan.
Right.
And if you go and measure the oxygen level coming out of your coming out of the kiln on a dry basis, then you go over to your ID fan and measure it, and it's twice as high. You know you got a real air leak somewhere.
A real air leak, right? So
you're just paying power to control that.
So, for example, like here on this red box, so this is a worksheet of the discharge in and the feed in, and we're looking at the exhaust gases at the feed in. So these are the densities that we calculate, the wet volume and the dry volume. And in this dry volume, we're looking at the O2%, right? And then this is 4.5%.
And in this case, it was 4.5
and
dry.
right.
But you can see wet in this case, it was 2.5. 2.5.
Right.
So you think if you measure it on a wet basis, you think you're doing just great.
Right.
But you're not.
Right.
So the water's diluting the oxygen level.
And then this you can directly compare with your O2 analyzer.
Right.
So here's some examples of...
Right. Well, I like to say we don't get into too much math, but it's really pretty simple. We do everything on a pound of fuel basis, and you just take pounds of CO2 divided by the pounds of fuel, and then that divide by the molecular weight.
And then you just add it all up.
And add it all up, and then go back. And you go add it all up, and then once you get the sum down there, you take the M CO2 and divide it by M sum and multiply 100. It gives you the percent volume. If you want it dry, you just take the H2O or the water vapor out of the equation. That give you the dry analysis.
Right.
And these are kind of important when somebody does an analysis on your kiln exhaust. Okay. Heavens, it's not the EPA, but whoever does it, you get an idea of where you're operating. If your O2 is too high, you're just wasting fuel.
Right. So this is a really good check on the health of your system.
Right. And that was the whole point. Now, there's some things you got to take into effect that if you're on the top of the Mount Everest, the gas flow will be considerably different than it will be in Panama City. Okay?
Right.
So we have you got to take into effect the elevation above sea level. And also the gas temperature, which is readily measured with the thermocouple inside the kiln. Stick that through the feed hood, and get a temperature, and then you take that into effect, the gas temperature, and then the density is just the pounds of CO2 divided by the pounds of CO2 divided by the total gas flow, which you can calculate readily. There's that molecular weight comes up.
Yes.
And the density factor is just the combination of the elevation and the temperature.
It's on the equation above.
Right. Once you get the density, which is you add all those up and get the density, and then once you get the density, you take the total gas flow divided by the density times 1,000, and that gives you a CFM.
And this is to get actual CFM, not standard.
Because you're not going to measure mass flow. You're going to be measuring
It's going to be very difficult to do that.
Right.
So this is just another worksheet. This is on the fuel side. So then once we do all this time we have all in the diagram we have all the numbers in there now.
Right. All the mass.
Mm-hmm. And then this is what we'll end up with by the end of our measurements, and we do all the calculations to where now we have a total system. Heat transfer, all the combustion, like we said in the beginning, all the stuff you're putting in has to go out somewhere. Right. So all the stuff in and all the stuff out has to match very closely.
Right. And that's really the whole point of this discussion is with the few measurements in the field, which you should have anyway. You can look at the performance of your kiln.
Right, and we can kind of figure out the health of the system with the kind of on the emission side. If you have carbon monoxide, carbon dioxide, O2, if there's too much O2, you may be wasting a lot of heat or a lot of fuel, and this is more related to the kiln. And then you can from this you can kind of figure out your process. Your process capabilities, like the quality of the product. If your product's not doing as well, then this may be a way to look at the symptoms.
Correct.
And then if you want to scale up to increase production, now you can kind of have a basis to scale up. So kind of the four main problems that we can help with this type of analysis is emissions, production, quality, and energy savings. Would you agree?
Correct.
Okay. So that's kind of, and that's what a heat mass balance does, is it can go through all that.
It really tells you your baseline operating conditions, which you may not really know.
Right.
You may know that if I do this, I get this result.
And this is all
but
based
you don't
on
know why.
And this is all based on the core principles. All the stuff going in has to come out, and it's mass or heat. Okay. So thank you, Roland, today for this wonderful discussion. If you have any questions, you want to contact us, we have our customer sales rep, Amber Martin, that you can email via opsamber@optimusps.com, or you can get a hold of me with email at tzhang@optimusps.com. This Amber Martin, and Tom Zhang's my name. You can reach our office at 844-880-5822. You can say, hey, can you get a hold of Amber Martin for me or Tom Zhang for me, and we'll forward that. They'll forward that to us. We're also social. So we have a Twitter link, a Twitter feed, YouTube, LinkedIn, and obviously our website, www.optimusps.com. So we look forward to our next webinar session. Thank you. Bye.